Okay, so here's the graph of the cardioid. How does this look like? You can plot this for various angles. When you plug in 0, 4 plus 4 times cosine 0 is 1, so 4 plus 4 is 8. You get 8 here. When you're at 90 degrees, if you plug in 90 degrees, then cosine 90 is 0, therefore you only get 4. So you get 4 here. Like half of this part. When you have 180 degrees, cosine 180 degrees is negative 1, so you have 4 plus 4 times negative 1, so it's 4 minus 4, which is 0. And then when you plug in 270 degrees, cosine 270 is again 0, so you get 4, but you're going 4 steps this way in the 270 degrees direction. So you're here. So those are the points that this graph must pass. And since you learned that a plus a cosine theta or a plus a sine theta, these give you the graph of cardioid. Just having these 4 points is probably enough for you to imagine what the entire picture looks like. The picture looks like it starts from here, goes like this, goes like that. It's the heart shaped, done sideways. Okay, for this one, what I want to now ask is, what is the area enclosed? Now, before I actually write the double integral to see how we do this, I want to write down 2 important trig formulas that you have to know in order to do any calculation here. It doesn't get used all the time, but a lot of times it gets used. So let me write those 2 formulas. First, sine squared of a is 1 minus cosine 2a over 2. And then cosine squared of a is 1 plus cosine 2a over 2.
What is this for?
We're going to use these formulas later. Okay. So let's write down the double integral. Here's how it works. You write down the area as integral of 1 dA. And the reasoning was this. You have z equal to 1, that's a horizontal plane, and you have some base area. So if you want to find the volume enclosed under this horizontal plane, it basically gives you this column-shaped thing. It's a cylinder, right? The volume of a cylinder is base area times the height, and because the height is 1, you end up with the base area of this thing times 1, which gives you the area, right? So that's one way to understand this formula. Another way to understand this formula is this happens all the time. Any quantity is the sum of its parts. So over here, if you wanted the area of this thing, you just find all the small bits of area for each points here, and you add them up over this area, this domain, then you get the area of the domain. So that's a very basic physical fact. Whenever you do, you use integrals to calculate something in physics, you've probably seen this a lot of times. In physics too, you probably seen something like electrical field E is integral of dE, or magnetic field B is integral of dB. Sometimes you integrate the mass by integrating the dm all kinds of integral formulas take this form. Okay? So that's another way to just understand this. All right. Okay, so that's the first thing you want to do. The next thing I want you to try is to rewrite this. Of course, 1 is just 1, but dA is what? In terms of polar coordinates, what's that? What is it? dA is? R, dr, d theta. That's what you need, okay? And then we have to figure out the bounds. You have to figure out what to put in here and here, right? And here and there. That's what we need. Okay. Now, in order to figure out those bounds, recall that for double integrals in rectangular form, we're using dx and dy, and I said when you have dx, you're painting rightwards. When you're using dy, you're painting upwards. That's how I explained it, right? But now we have something new. We have dr. What would that mean? It's an increment in the radial direction. So what do you think? You start from the origin, go radial direction. That's what dr means. Okay. Now, if we paint this region using this radial direction brushes, where does the brush begin? At 0, right? So it begins at 0. And where does it end?
Get the 4 plus 4 cosine theta.
We end here, right? We begin at 0. We end wherever this curve is met. Okay. Right. So we put 4 plus 4 cosine theta. Okay. And then what about the thetas? It goes all around the circle, right? So it goes from 0 all the way around 0 to pi. And if we compute this, that's it. That's how you get the area. Okay, now let's try to actually do the computation. If you integrate r, this is 1/2 r squared. And you're plugging in 0 and 4 plus 4 cosine theta, right? You still have to integrate by theta afterwards. Now, this goes into the r, this goes into the r, and if you subtract, you end up with the integral 0 to 2 pi. When this is plugged in here, it's 1/2 of 4 plus 4 cosine theta. And then you have to square it. So you have to do this integral. Okay. All right, let's expand this. I should pull the 1/2 outside so we can worry about that later. If we expand this, this will be 4 squared will be 16. 4 times 4 cosine theta is 16 theta, but 16 cosine theta, but we have to double it, so it's 32 cosine theta. And we squared the last one, which is 16 cosine squared of theta. So we have to integrate this. Now, if you see this integral, this is easy. That's easy. How about this one? How about this one? That's not hard. That's not easy. It's cosine squared is something that's not easy to integrate. You have to use this. That's why I wrote this formula down. Okay. So in our case, I have cosine squared of a with a being theta. So what do I put here? (16 plus 32 cosine theta plus 16 times 1 plus cosine 2 theta over 2. That becomes 8. which gives you 1/2, 0 to 2 pi. 8 times 1 is 8, plus 16 gives you 24. 32 cosine theta, and then 8 times cosine 2 theta. That's what you have. Okay, now let's continue. Then it's all easy to integrate. 24 integrates to 24 theta. What's the integral of cosine theta? Sine theta. Integral of cosine 2 theta? 1/2 sine 2 theta, right? So don't forget, if you have some number here, when you integrate, the reciprocal must appear here. And then you plug in 2 pi and 0. And luckily for us, when you plug in 2 pi into sine or sine 2 theta, it's all what? What's sine 2 pi? 0. Sine 4 pi? 0. So that's gone. And also when you plug in 0, everything is 0. The only time you don't get a 0 is when 2 pi is plugged in here. So you end up with 1/2 times 24 times 2 pi. 1/2 and 2 cancels, and you get 24 pi. Done. Okay? So that's the integral.